Today we are starting our fourth and final chapter on physics for the year. It's a pretty short chapter. It's just about work and power and machines. And we're going to cover work and power pretty quickly right away now. A lot of you think you know what work is, and I would agree with you. The scientific definition of work, however, is probably not what you think of work is. I'm with you. I don't really like the scientific definition, and I'll show you an example why, but we have to use the definition we have. So what is this scientific definition? Well, in science, work is done when a force causes an object to move in the direction of the force. It's a transfer of energy. Okay, so the force causes the object to move in the direction of the force. So are you doing work if you pick up your book? Well, yes. The book moved in the direction of the force. What if you now walk with your book across the room? Are you doing any work then? The answer is no. The force direction and the movement direction are different. Okay, this is where I don't really like the scientific definition of work. Imagine that I have a 100-pound bag of concrete, and I lift this bag of concrete up and I put it on my shoulder, and that was a lot of work. Okay. Now I stumble across the parking lot from Lowe's to put it into my car, and it's hard and I'm sweating and it's horrible, but technically I'm not doing any work because the direction of force is different than my movement direction. Okay, so that's kind of why I don't like the definition of work, but that's what it is. Okay, the movement direction and the force direction have to be the same. So is work done every time the force is applied? Well, no, of course not. Okay, and there's an example there. There has to be movement and it has to be in the same direction. You could be applying a lot of force but not be doing any work. Okay, so again, work is done on an object if the object moves as the force is applied and the direction of movement is the same as the direction of the force. So work, yes or no? You push on a car but are not strong enough to move it. Okay? No, it didn't move. Okay, remember that the object has to move. How about you toss a pen straight in the air? Yes, until you let go of the pen. After that, you're no longer applying a force. Okay, so while you were touching it and lifting it, to throw it in the air, it was going in the same direction as the force you applied. But once you release it, you're no longer applying a force, so you're not doing any work on it. What if you pull your brother along in a wagon? Okay, this is a little bit tricky one. Okay, so let's say I have my wagon here. There's my wagon. Here's my little brother. Okay, and I'm pulling him. So my force, I'm applying a force in this direction, right, to pull him. Okay, his weight is mainly going down. Okay, so you'd think that would be different. Okay, and that's what a lot of places are. So if you look this up on the internet, you'll find lots of places say, nope, not doing any work in this situation. Other places say, yes, you are doing work because the wagon, okay, is moving in the same direction as the force, and his weight is pushing down on the wheels, causing friction, so you have that force, so you actually are doing it. So it's kind of a tough call. I like to just say, yeah, you're doing work. He's moving in the same direction as the force. But it's kind of a tricky example, and like I said, if you look around, you'll see different answers for that same problem. Okay, how do we calculate work? The amount of work done is the force applied multiplied by the distance through which the force is applied. So it's simple. Work equals force times distance. Force is usually going to be measured in newtons and distance in meters, so work will be in joules. A joule is a newton meter. Okay, so a joule is a newton times a meter. Because work is a transfer of energy, a joule is also used to measure energy. And we'll talk about this later when we're talking about energy. It's still going to be in joules. Okay, so do you do more work hiking up a long but gentle winding path, or climbing up a sheer cliff. Okay, so here's my long winding path going up here, or the sheer cliff right here. You get to the top here. In which way are you doing more work? Technically, the amount of work is the same. The amount of work not only depends on force, but also on distance. The cliff climb took more force, but happened over a short distance. The path took little force, but was long. And here's kind of how they write it. F1 times D1 equals F2 times D2. So if you say the cliff climb here, okay, so this cliff climb, that's going to be your F1 D1. Okay, so it's going to be a lot of force to climb up the cliff, very hard, very difficult, a lot of force, but it's a small distance. So a lot of force, little distance. And that's going to balance out with here, so this long winding path, that's going to be this side. Okay. It's going to take you very little force to climb up that, because it's a nice and gentle slope, but a lot of distance. Okay. So big force, little distance equals little force times big distance. Okay. They are going to average out to be the same. And we're sticking with that to the same right now because they got the same place. In another couple days, we're going to be talking about simple machines, and this is basically an inclined plane. And technically, this long winding path was a little bit more work because of friction. Okay, with more distance, there was more friction. But for now, we're saying that the work was equal. The big force times little distance equals little force times big distance. Let's do a few examples. A box weighs 6 newtons. You lift it 1.5 meters. How much work? So the formula, work equals force times distance. So work equals 6 newtons times 1.5 meters. That will give you 9. And because we had newton meters, we have a joule. Okay, so 9 joules. Boris Becker swings a 1 Newton tennis racket 2 meters. Okay, is he doing work? Yes, it went in the same direction as his force. So how much work is he doing? Again, work is just force times distance. So work equals 1 times 2, which is 2 joules. And again, 2 Newton meters is the same as 2 joules. Work isn't very hard. Power is simply how fast work is done. Okay, technically the definition is the rate at which energy is transferred. Okay, realistically, power is how fast work is done. To calculate power, just divide the amount of work by the time it takes to do the work. Okay, so power equals work divided by time. The amount of work divided by the time it takes to do it. The unit is most likely going to be a watt. Okay, a watt is a joule per second. Okay, so as long as you're doing joules and seconds, you'll have watts. Obviously, the faster work is done, the more power was required. Okay, because you have a smaller time, so you're going to have more power. A couple examples. What is the power of a small motor that can do 4,500 joules of work in 25 seconds? So we know our formula, power equals work divided by time. So power equals 4,500 divided by 25 seconds. Okay. That will give you 180 watts. And that has 2 significant digits, so it's good. Okay, 180 watts. The next example, a light bulb is on for 12 seconds, and during that time it uses 1,200 joules of electrical energy. What is the wattage, the power, of the light bulb? So again, same formula, power equals work over time. So the power equals 1,200 divided by 12, which is 100 watts. Okay, 100 watt light bulb. Yeah, okay, it's a fairly standard light bulb for an incandescent light bulb. We're going to talk about light bulbs in class and talk about LEDs and compact fluorescents and the regular incandescent light bulbs. 100 watts of energy is what that light bulb took, and LED equivalent brightness would be a lot less. Last one, I pulled my cat in a wagon that weighs 80 newtons combined, okay, cat and wagon combined, for 30 seconds. And we went 20 meters. How much power did I expend? Well, first thing we have to do is we have to find the work, and then we can find the power. So work, again, equals force times distance. So the work equals 80 times 20, which is 1,600 joules. Okay. Now that I have the work, I can find the power. So power equals 1,600, your work over time, and the time was 30 seconds. So I divide 1,600 by 30, and I get, it looks like 53.3333, which we're going to round to one digit. It looks like from the 31 digit to 50 watts. Okay. So a two-step problem there. I had to find the work first, and then once I had the work, I could find the power. And you'll have to do a couple examples like that. Like I said, in class, we're going to talk about light bulbs. We're not going to do it here. And really just compare. We have incandescent light bulbs, compact fluorescent light bulbs, and then the new style are LED light bulbs. And we're going to compare the efficiency of them with the energy, so kind of the wattage that they use. Okay, we're going to do that in class, and we'll have a little chart we can compare and see which ones may be better cost-wise. And that's it for work and power. Okay, most of the unit, and all we have to do is talk about machines.